In the 18th century, a book was published in Germany with a tale of a baron. And it was, I think, meant to be a sort of satire for the crazy, hard to believe stories that some of these war heroes would tell. And some of the exploits of this fictional character called the Baron of Münchhausen included, for example, fighting a giant crocodile or riding a cannonball. I think you can see that down here. The one that I'm interested in right now is there's a passage in the book in which he's riding his horse and he accidentally rides it into a mire, which is a wetland, a sort of bog or a swamp. You can see it down here. And he's stuck and his horse starts to sink. But of course, since he is the Baron Münchhausen, all he has to do is he's so strong that he can just pull himself out by the hair, including his horse, saving both of them, right? Now, why do I care about this? Well, obviously this wouldn't work in real life, right? In real life, he wouldn't be able to pull himself out without standing on solid ground, regardless of how strong he is. And this begs the question, well, what kind of ground is math built on, right? Because if we cannot answer this question, then maybe we are falling into the same category of satire or fiction as the Baron Münchhausen, in the sense that we are pulling ourselves out in in a more theoretical sense, right? And by the way, if you're watching this on YouTube, I can share the PDF and you can just click on the link. A video that I recommend that expands upon some of these topics, but is slightly out of the scope of the course, is in the green triangle on the top right of my screen. Okay, so what are the foundations of mathematics? And this is the very first chapter of the course. And let me give you an example. You probably took something, a course on calculus or maybe linear algebra, or at some point someone mentioned a concept, right? An object in math that you defined and then you proved certain things around it, or you try to decide whether some object satisfies that condition or not. And the example I choose for this, in this case, is a continuous mapping, right? And maybe you've dealt with children who are very curious and they keep asking, but what is that? But what is that? But what is that? And so on. So we can play this game with any object that gets introduced in math. Let me turn off my camera. We could play this game, for example, in continuous mapping. Someone would ask, well, what is that? How do you define a continuous mapping? And then, well, you would have to know a little bit about limits, and then you would say that a function that commutes with the limits and such that for all epsilon and so on. And then, okay, well, you use the word function. What is a function, right? And as we will see today, a function is just a special type of relation in which something and something and every element gets unambiguously mapped and so on. Okay, but you use the word relation. Well, what is a relation? And we can do this forever, right? That's more or less the point. Now, my question to you is, this sequence of questions must at some point hit the bottom, right? Or rather, the sequence of answers. And when does it happen? And the tale of the Baron Münchhausen inspired what is known as the Münchhausen trilemma, which postulates that every statement, every truth, including mathematical ones, must fall into one of three categories. It is either circular, in that I will eventually, for example, in the case of a set, which would is what I suggest would be the bottom of the sequence of questions. If you ask me what a set is, I would have to tell you, well, a set is a collection of objects. And then you would say, well, what is a collection? And then I would say, well, it's like a class of things. And you would say, well, what is a class? And I would say, well, it's a set. And I go into a loop, into an infinite loop, right? So that would be a circular reasoning. Another possibility is that this sequence of questions is actually infinite and you never reach a bottom. So that's another possibility. And finally, the third possibility postulated by this trilemma, by this thought experiment, is that truth is eventually dogmatic, right? I will eventually come down to something that I am unable to justify, and you just have to take on faith. And that's what axioms are, right? We don't prove axioms. We don't, derive axioms from other axioms. The point is that they are independent, and then we just have to assume that they are true, and we have to play by the rules. Okay, so like I said, what I want to convince you of as the introduction to set theory is that the bottom of these questions for pretty much any mathematical object you are likely to encounter, unless you take something really exotic like category theory, is the concept of a set. And the set is the most primitive object in mathematics in the sense that everything you've probably ever mentioned is a set in a sense, right? A continuous mapping is just a set. An integral is just a set. Everything you've talked about is probably just a set. Numbers are just sets in essence, even if we don't treat them that way, because it might not be useful in the particular theoretical framework that we're working in. Okay, so that's it. How do we define a set? What is a set? And if you understood what I just said about the trilemma, well, we can't really define that. What I can tell you is how sets behave and how we can use them, how we can make use of them by giving you essentially a list of axioms that describes everything about their behavior. Now, I find this pretty interesting and quite insightful because think about it. It means I can tell you everything there is to know about a set, except what it is in the first place. Okay, now you might say, well, we don't really care about this. This is like an epistemological problem, right? It's more a thing of philosophy rather than mathematics. Why do we care if these sequence of questions hit the bottom or not, right? Whenever you are proving or working with continuous mappings, you never ask yourself, but what is this? What is that? All the way to the bottom, right? You just work with the definition of continuity, and maybe you have a particular example of a function like f of x equals x squared, and you can prove that that is continuous by taking limits. You don't really care about going all the way down. So let me just give you an example that might hopefully convince you that this is more problematic than it might seem, and it actually caused a sort of historic crisis within mathematics around 100, maybe 150 years ago. Okay, so if we tried to answer this question of what is a set, you might be tempted to use something like this. And please let me know if there's anything unclear about what I'm saying. So you might be thinking that a set is just anything that you can write in these curly brackets, any object x, and you can impose any condition that you want on x, right? So for example, the collection of all numbers or all real numbers, if I'm talking about real numbers or rational, whatever, that are bigger or equal to 1. That seems to be a reasonable set, and you can draw it, and if I give you another real number like 2, then you can decide if that is an element of the set or if it is not an element of the set, like 0, for example, right? So it might seem that I can write whatever I want here, right? I can even write nonsensical things. And by nonsensical, I mean things that are correct in grammar, but are just always false. For example, here's another condition that I can impose on a set, right? All the elements x such that x is different from x. Well, we know that the equal sign behaves like an equivalence relation, if you followed my previous lecture. So this is a valid set. It just doesn't contain anything, right? Because no element is different from itself, obviously. Okay, so it would seem that I can even write things that are always false. But now my question to you is, can this literally be anything? Can I really write anything I want in this part of the definition? And if not, then what are the rules that I need to follow in order to make sure that I'm actually defining a set? I will not really answer this question because that is axiomatic set theory, but if you're curious, I can provide some references for you. Also, we won't need it. It would get really technical, but I just want to convince you that this is something worth thinking about. And here is the condition that I will impose now, okay? So recall that this symbol, this is a lowercase epsilon, but it is slightly written slightly differently. That is the belonging relation, right? The belonging relation. So we say that X is an element of a certain set. So this seems reasonable, right? This has no grammar errors in the sense that I'm not just combining symbols in a way that doesn't even produce a word in the mathematical language. This is a valid word. It might just always be false. Okay, so this is a valid, it would seem like this is a valid set. And if it isn't, it's not clear at all why this shouldn't be a valid set, right? So this is a set. Consider the following set. Consider the following. And why don't we give this thing that I just defined a name? Maybe, I don't know, capital X. By the way, when I'm writing on the board, like handwritten notes, I will add these two horizontal lines to X to distinguish them from the lowercase x. Some people make lower x like this, capital X like that. I don't really like that very much. So just keep in mind this is just a letter. That's just uppercase X, okay? So now my question is, can we say anything about whether X is an element of itself or not? First of all, I'm pretty sure you've never seen an example of a set that is an element of itself. So your intuition should first tell you, this probably doesn't happen, right? The belonging relation is not only not reflexive, it is not reflexive on any element, right? You shouldn't be able to find a set that is an element of itself. What would a set like that even look like? And you might be tempted of writing something like this. Maybe you have a bunch of curly brackets, and if you have infinitely many of them, then maybe this can be an element of itself, right? Anyway, I will let you think about whether you can find a set that is an element of itself or not. And if you can't, then why not? But that's not really important for the question that I just asked. So it seems like we don't really know how to answer this. It seems a bit abstract. It seems like we just have to plug in things to the formula and see what happens. So let's just do that. I think I have enough space here. So x if x were an element of itself, which we don't know if this is true, but let's assume that it is, and maybe we arrive at a contradiction, and that would answer the question. So if x is an element of itself, that means that it satisfies the property that defines x, right? But the property that defines x is not being an element of yourself. So if x is an element of x, then this immediately contradicts the sentence, right? Then x is not an element of x because it satisfies the property that defines x, capital X. Okay, so this is a contradiction. Contradiction. I will write proper proofs in the future, in the near future, just a few minutes. This is just an example, right? So this is a contradiction. And the thing we assumed that produced the contradiction was that x is an element of x, so that can't be true, right? X cannot be an element of x. But this is also problematic because if x is not an element of x, well, then x satisfies the property that defines capital X, right? Actually, let me move this. And for those of you paying attention, you might see why this is kind of weird, right? Then x is an element of x. Also a contradiction. Okay, so in both cases, I arrived at a contradiction, which means that the thing that I assumed is false. But what did I assume? Because I covered all cases, and these cases are mutually exclusive, right? I should be able to decide either x is an element of x or x is not an element of x, and there are no other possibilities. There is nothing in between, right? Relations are all, the ones we've seen so far at least are binary. It's either true or false. So which is it? Is it true or false? How do I resolve this? It seems like I just broke math. Does anyone have any ideas about this? Feel free to write them in the chat. Okay, exactly. So X cannot be a set. I agree with that. I agree that X is not a set. And this begs the question, well, if X is not a set, even though it seems so simple and reasonable to define a set like this, then what is a set, right? Can you give me a complete list of rules that will for sure always work and never produce a contradiction like this? Because here the contradiction was evident. I could write it in one sentence. But what if you define a weird set for me with like a lot of conditions, and that set will produce a similar contradiction, but maybe I need 200 pages to prove that contradiction. How do I know that will happen or that won't happen? And the interesting thing is that we can't really know if that will happen or not. And if you go back to the recommended video, I think maybe they don't mention this explicitly, but they mention something similar, which is Gödel's incompleteness theorem, right? And there's two theorems, and the second one says that an axiomatization like the one we're dealing with here in set theory is cannot prove its own consistency. So I cannot prove to you that with the rules that we're playing, I will not be able to arrive at a contradiction. So that is quite interesting. And we will mention more about this as we move on to the more advanced set theory chapter, which is chapter, I don't remember, 3 or 4, one of the later chapters, I think, after the short summer break. Anyway, if you're curious about the thing that I just explained, then you can find the references Russell's paradox, and there's a long Wikipedia list of articles about self-reference paradoxes that is quite interesting, and I suggest you take a look at. And I also mentioned the trilemma. I'm just including this in case you want to read more about that. Okay, so now we can get started with actual sets. And like I said, I won't define what a set is to you, but I will give you rules that we're going to be able to build a theory on. Okay, so now for the actual, we leave the realm of philosophy and we start with actual math. So the first definition I have for you is something that you probably already know. We say that a set A is a subset of some other set B, and we denote this with this rounded less than or equal to sign that you can see here. If for every x, being an element of A implies that you're always an element of B, right? And some basic properties is that for any sets A, B, C, every set is a subset of itself. That is reflexivity, right? This is a relation, even though I haven't properly defined relation. I mean, I did it last lecture, but so this is a reflexive property. Now, the empty set, which is the only set with no elements in it, will be contained in every set. If you're talking about relations in the context of order, then this means that the empty set is like a minimum element. It's the smallest element in the universe of sets, right? Because it is less than or equal to every other thing. So sets have a minimum element. Now, this is in the context of relations. In the context of logic, this is also called a vacuous truth. It is something that is true just because you cannot find any counterexamples to it, because you cannot find any element at all, right? Now, I will explain this in a second. The third property is transitivity, right? If A is contained in B and B is contained in C, then of course A is contained in C. Now all of these are very short proofs, less than a sentence. It's just a direct application of the definition. So I think I will only focus on the one that might be weirder to you to write down. Let me add one more, since we're already doing this. Okay, just a second, I can do this nicely. And if A is an element, sorry, is contained, not an element, is contained in B and B is contained in A, then the sets must be equal. And this is, of course, an if and only if condition, because part 1 says that every element is contained in itself. So if A is equal to B, then in particular, A is contained in B and B is contained in A. I won't write that down because I would be repeating sentence number one, property number one. Okay, hope this makes sense. So this order relation that is containment, this one that I just defined, this thing right here, is reflexive, it is transitive. Both those things define an order, right? And you can ask yourself, all the properties that I defined on relations, this is not generally symmetric, right? If A is contained in B, there's no reason to expect a B being contained in A unless they are the same set. So it is not symmetric, but it is more than not symmetric. It is actually the opposite. It is anti-symmetric. Now, you don't need to know all of these things. You don't need to memorize all of these things. In case I ask you to prove something like this on the final, I would remind you what reflexivity is. Of course, some of the more important concepts like an equivalence relation, I would expect you to know how to prove that something is an equivalence relation without having me to write the definition. But all these tiny definitions that I'm writing down, you don't need to know. Okay, so antisymmetry means that the only way that two elements can be related in a symmetrical way is if they are the same element, right? Antisymmetry, so you don't have any sort of symmetry in general. Okay, so this is the most important thing you need to know about the subset relation. And maybe let me add some words as to why, for example, property number two is true. Like I said, the other ones, if you just write down the definition, it follows immediately from it. So let me shift this down a few sentences. Hopefully that worked. Okay. Takes a lot of processing power to shift down a few lines for some reason. So this is the first proof we see in the course. And let us do two and rest this exercise. When I when I say that something is an exercise, it typically means that it's either too technical or boring to be covered in the lectures, right? It's just writing down something that contains ideas that we already saw in some other example. And it's also not interesting enough to be in the problem set. So you should still think about these exercises, right? These are all good candidates for something to appear on the final. Maybe not something as simple as this, but if you want more practice problems, then this is a great source of problems. And if you're struggling understanding the concepts, then this is also good practice to write down the proofs and expand the definitions and seeing if you can make sense of them. Okay, so how do we do number two? Number two is claiming that the empty set is contained in every set A, right? Okay, so to do number two, we have to say let A be an arbitrary set or just be a set, because we're proving a statement of the form for every set. I mean, technically for every set A, B, C, but B and C don't get mentioned, so I don't care about that. For every set A, the empty set is contained in A, right? Okay, so we say let A be an arbitrary set, and now we have to prove that the empty set is contained in A. Now, if you scroll up to the definition, A being contained in B mean that for every X, something happened. So it's another for all or for every statement. So I have to say, let X be an element, right? Sorry, not an element, anything. Let A be a set and let X, or let's say, let's take to change the word. Take an arbitrary X, right? Basically, we took capital A and X. So now we have to show that X being in the empty set implies that X is in A, according to the definition. So since we're proving an implication, the easiest is to assume that the antecedent is true, and then we try to conclude the, well, conclusion of the implication. So suppose that X is in the empty set, right? But this is obviously false because the empty set is defined by the property of having no elements. So the belonging relation is always false whenever you put the empty set on the right side. Suppose that, okay, this is false. So X being an element of A follows from this. If you assume something false, then you can prove anything. So if we assume that X is an element of the empty set, well, then we can conclude anything we want from this, right? There's a nice German phrase that summarizes what I just said. If you find this style too confusing, there's another maybe better way of writing this. So instead of assuming something false, maybe I can change this and just say, notice that X being, it's the same proof, right? Everything I wrote is correct. I'm just editing this for clarity. So notice that X implies X in A because X in empty set is a false statement. And any implication starting with something false will be true, right? If you want, this is not part of the proof, so I will write this in a different color, which hopefully you can see. If not, maybe I should write this in parentheses. Okay. I think that's how you spell it. So that's a German phrase that just says if you're assuming something false, then you can prove anything, right? Anything you want, basically. Okay, why is this true? Why is an implication with starting with something false always true? Well, if this weren't true, if it weren't true that the empty set is contained in A, then I should be able to produce a counterexample, right? So let me just write this as a period, and then I will close this off since this is the end of the proof, right? This is the end of the proof. But let me maybe add a comment. So alternatively, another way to prove this by contradiction, right? If we assumed the contrary of what we want to prove by contradiction, if we assumed, what is the opposite? It means that, sorry, the empty set is not contained in A. Well, what does that mean? It means that instead of for all X, if X is in the empty set, then X is in A, the opposite happens, right? So then there must be a counterexample. There must be some X that is in the empty set, but doesn't satisfy the conclusion, meaning it is not in A. And you can see this is absurd, right? How can I conclude that there is some X in the empty set? That never happens. So this is a contradiction. Because no matter what X is, X can never be an element of the empty set, right? Like I said, that's what defines the empty set, even if I didn't explicitly write it down. Okay, so this is an alternative proof. Maybe I should add a small, I think this symbol, this square, is called a tombstone. It symbolizes when the proof like dies. Don't quote me on that. Okay, next definition. Let's define some more operations on sets so that we can work with them. This is basically just a toolbox that we will expand and develop over time. And we don't really have that many interesting examples yet because we haven't built any theory. All the examples we have are purely set theoretical. So just be patient. We will see more interesting things over the next few weeks. Okay, let capital F or what is it? Like a curly F be a family of sets. And if you believe what I said earlier, that everything is a set, then I'm not really adding information by telling you that this is a family or a collection or a set of sets, because it is just a set, right? Every element of a set must itself be a set. Now, I'm adding this as a comment because it's not really important. We will always think of F in this context as just being a family of sets. And I will give you examples. I know this might seem a little bit abstract. I will give examples of this in a second. So the union over F is the set of all elements that belong to some element of F, right? So if F is a collection of sets, then the union of f is everything that is in some of those sets, in at least one of them. And this symbol right here is the existential quantifier, right? This just means there is. So let me add this. There is. There is. Now, similarly, the intersection of f is the same thing, but I have to flip the other quantifier, and this means for all. We will add details about what this means in a second, right? And this, I know for some of you, it might be the first time studying these quantifiers. Okay, so for the intersection, I do need the family to be non-empty, and you can think about why that is needed here. But it's not too important since I will typically not intersect weird things for you, okay? So here's notation that's probably more familiar to you, and it's the one we will work with the most. So if this definition seems a bit abstract, then don't worry. I will show you that this is something that I'm sure you've seen in the past, right? So look at the example number 1 that I have written here. Take the example where the family F contains exactly 2 sets, capital A and capital B, okay? I am reading this line right here, capital A and capital B. What would be the union over that set? It's the set of all elements that belong to some element of the family. That is, they have to either belong to A or belong to B. And this is what I wrote right here. That's the definition. And a more friendly notation for this type of family, when it's just a finite family, is I can just write the U for union in the middle of the 2 sets, right? So instead of writing it like this in a weird way with the curly brackets, I can just say A union B, right? But this is the same definition, just in a more particular case when the family has 2 elements. If you look at example number 2, it's the same thing. Now I have 3 elements, right? So what is the family ABC? What is the union over that? Well, that's just A union B union C, correct? So it's the all the elements, all the objects X such that they're in either A or B or C. Maybe they're in more than one of them, right? A, B, and C could all be the same set. This doesn't matter. And this works. Now, if you want a more sophisticated example, oh, and I should mention that you might be wondering, how do you know that it's not like this, right? Like, how do you know which union to take first? But of course, something that is trivial to prove as well follows directly from the definition, is that parentheses don't matter. This operation is associative, right? You can do it in any order you want. It's also commutative, right? So A union B union C will produce the same result if you do A union B first and then add C, or if you do B union C first and then add A. And you can also do A union C union B or C union B union A and so on. I think you get the idea, right? I won't write all this down because it's very technical and it's things that I'm sure you've done in the past, but I'm happy to expand on it if you want me to. Here's a more sophisticated example. At the bottom of the screen, you can see an index family. So what if we have a family of sets that contains infinitely many sets, right? For example, A0, A1, A2, A3, and so on. We can index them by the natural numbers. So what would be the union over that? Well, for a more convenient notation, we typically write the index under the union symbol like this, or something that I'm not a huge fan of, but you can also see written in some places. It's like this, right? You let the index run from the smallest index to the largest index, or just include the symbol of infinity if there is no largest index. And this would simply be the set of all elements that are in either A0 or A1 or A2 or and so on, right? They must be in some A sub n. And all of these examples make sense if you substitute the intersection. If you put in the intersection instead of union, and I think that's most of the abstract examples on notation I want to cover. I will give you some more concrete examples about these operations. So look at number 5. And for this, I'm assuming that we already know what the natural numbers are. So you can just use your working knowledge of them. We won't really construct them in this course, but we will talk about them in a subsequent lecture. But for now, just consider this to illustrate an example. So the family of sets that I am indexing are of the form 0, 1, 2, 3, all the way to n. Each one of those is a different set, right? The first set contains just the number 0. The second set contains the numbers 0 and 1. The third set 0, 1, and 2, and so on. So this is an infinite family of sets. And if I take the union over them, what do you think we'll get? Is there an easier way of describing the set? What do you think? What do you think I get if I take this union? Okay, yes, I have some there's some answers in the chat, and they're all correct. This will be the set of all natural numbers, right? So indeed, if I take this union, well, this should be everything, right? Let's prove this before we go to the next example. How many did I even write here? Okay, that's fine. So let's prove this. How do you prove that two sets are equal? Well, two sets are equal if they are contained in each other. So the easiest way might be to just prove it that way, right? So something that aids in separating paragraphs is adding the symbol of what I'm proving. So if I'm proving the forward containment, you have to take any element on the left and prove that it is on the right, right? So let M be some element on the left. What does this mean? What does this mean? It means that then there is n. By definition of union, if you take something in the union, it must be in some of the unions, right? In some of these sets. So there is n such that m is in that particular set all the way to m, right? But 0, 1, 2, 3. Sorry. Yep. Go ahead. Does anyone have a question? Okay, feel free to write it in the chat or just unmute yourself. Any one of those options is fine. Okay, small typo. This is of course n. Now the numbers 0, 1, 2, 3, all the way to n are of course natural numbers. So this is just contained in n, right? But in particular, m is also an element of this. So we're done. This is the first containment, left to right. This was the easy one. Let's maybe do the other one. So this one is a bit harder. Let m be a natural number. How do you prove that it is on the left side? And to prove that it is in a union, you have to exhibit a union that contains m, right? So let m be a natural number. And then how do we find a union, an appropriate union? And this is actually easy if you do this. Then m is obviously contained in the set that contains everything up to and including itself. Now I could stop here, but I could obviously continue, right? I could do it, maybe add two more elements. It doesn't matter. I don't have to find the smallest one, and it will be contained in infinitely many of them. So I can pick any one I want. Just for the sake of clarity, maybe I should pick the easiest one, which is this one. And this is a union of the set. So it is of course contained in the union of all of them, and we're done. So we're done, right? And this is how you prove a double containment. There's some details that I'm saying out loud verbally, just because I don't have that much space, but this is a perfectly valid proof, okay? What about the second, sorry, the example number 6? What do you think that union would be equal to? This time, so in the example 5, the sets are growing in size, right? For every bigger n, these sets contain more elements. In the example 6, all the sets contain exactly two elements, namely n and n plus 1. So what do you think this union is equal to? Okay, let's see the chat. Yeah, still all natural numbers. Correct, correct. We will see more sophisticated, more elaborate examples in the future. I just want to cover the very basics of this. I don't think we have to prove this. It's very similar. So this proving this would be, let's say, left as an exercise. And yeah, I see all of you already figured out that this is just the natural numbers. What about exercise 7? Can you tell me what you think number 7 would be if we take that union? And as you see, I'm using different notations for the same thing, right? Here I'm using the notation n from 0 to infinity, but I could have just indexed it. I could have done something else. In fact, maybe just to have all examples of notation, maybe I can, mm, you know what? It's okay. Let's just let's just keep things simple. Exactly. Very well done. So this will be the set of all even numbers, right? And one way to write it is this is the set. I could just write even numbers. We probably know what that means. But if I want to be a bit more formal, I would say it's the n's such that you can find a k for which n is 2k, right? It's all the things that are 2 times something. And now that I think of it, if you want to prove this on your own, maybe this changing the variable names will make this a lot easier, right? Because then n will match the n you will need for the containment. Let's say this is also an exercise. I think all of you figured this out, so this is just, these exercises are not that important, right? They're just practice writing proofs. I missed this parentheses for some reason. Okay. Okay, any questions about this? What is the next thing? Okay. So maybe I can add a few more details, a few more things that can be said about this. Okay, I see no questions. That's fine. Okay, so the next definition is something that I mentioned in the previous lecture, right? The power set is the collection of all subsets of some set, right? And it's denoted by this calligraphic P. I will also define to you the difference of sets, right? A minus B, set difference, right? This is a set difference. You subtract a set from another. And it's all the elements of A that are not in B. And keep in mind that B and A need not have any relationship among themselves, right? We don't need A to be a subset of B or the other way around. A and B could be anything. And also A cross B I defined last time. This is the Cartesian product of two. Cartesian product, let me add that. So in the remaining minutes of the first half of this lecture that we have, let me tell you about how to summarize a lot of the things that we just saw about the union intersection, the set containment. And this is an object that I will not define to you, but I will mention many times in this course. And I will not define it because we will not really study it abstractly. We will only study these particular examples of this. Although I think some of the additional problem sets, the problems that aren't marked, use these concepts. By the way, the same way that I have a union for two sets here, but I defined it way more abstractly by taking arbitrary unions over possibly infinite families. There is an analog for that for the product, right? The product of sets can be defined not just for two sets, but for many sets, not just finite, but infinitely many of them. And there's at least one extra problem that there's at least one extra problem that sorry, I got distracted. That uses this. So I think I don't have to write that down right now because you don't really need it, but just keep that in mind. Okay, so I just got a question in the chat. What do those symbols mean? Okay, so let me scroll up and clarify this. So when I'm writing a proof, the question is, what is this? Maybe I should add this as a comment. So what do these mean? These are just the containment symbols, and I'm writing these in a small box to help the reader figure out what I'm proving. Instead of saying, let us prove that this and that, I just add the symbol, right? So the proof that I'm writing is a double containment. I have to prove that the left is contained in the right and in reverse. So to help the reader figure out which part I am writing without having to add a lot of clutter, I just add the symbol. And this symbol says, okay, for this sentence, the thing that follows is the proof that left is contained in right. And the thing that follows this symbol is the part of the proof that shows that right is contained in left. And if you have those two things, then by one of the properties we defined above, the sets must be equal. And so I'm done with the proof. Yes, yes, you're welcome. And yeah, okay, so another important question is if you are allowed to use the same notation. Yes, yes, you're allowed to use the same notation. Especially during the final, where it would help you save space instead of writing, let us prove that this and that. These symbols can help. Other symbols that can help is if you're trying to prove an if and only if, sometimes you use this symbol, right? I'm proving the forward implication, I'm proving the backward implication, and then there's no need to write, let us prove that this and that, you know? So it all comes down to how we want to write proofs. If you're writing a textbook, then maybe you would want to avoid using symbols as much as possible and writing in English. Okay, so the next question is, do we always have to prove both sides? Not necessarily, right? I think there are some examples here maybe where it's just a containment, and then you just have to prove one direction. There might be the case that one containment is obvious from the context, so there's no need to write anything down. But yeah, we'll see more examples about this. It is possible for you not to have to prove both. Okay, so here I want to summarize everything we've said so far about this. Yes, you're welcome. Okay, so what kind of structure is this, right? If you take the power set of a fixed set X, and we can look at some particular examples, what is this relation, containment relation on the set, right? How does it look like? Well, we already know one thing. We know that the empty set is contained everywhere, and it is also an element of the power set. So maybe if we want to write things like up and down, where should I do this? We can say the empty set is all the way down here, and it will be contained in everything. Okay, let's maybe do a concrete example. Maybe that will be more helpful. So let's do the concrete example. How concrete should we make this example? Let me think about this for a second. Okay, why don't we take X as the set of all natural numbers so that it's an infinite set, right? So yeah, let's do this example. So the smallest set is always the empty set that is at the very bottom. And the next set I could write that is contained would be the singletons, right? The singletons, they all contain the empty set. And there's nothing in between. There's nothing between a singleton and the empty set because you cannot have fewer than one element, but more than zero elements, right? So these sets are here. The lines that I'm drawing denote containment, right? So if I draw a line from bottom up, it means that the bottom is contained in the one that's at the top. And of course, I have infinitely many singletons. I have one for every n, and they just go on forever, right? There's more sets here, obviously. For example, the set containing 0 and 1 is containing the singleton of 0, and it contains the singleton of 1. There's a set of all even numbers, right? The set of all even numbers. Maybe you can write it somewhere here. So this is a set of even numbers. Let me just use this notation. This one will contain the singleton of 0. It will contain the singleton of 2, the singleton of 3, sorry, of 4, not of 3, and so on. It will also contain things like the multiples of 4, right? So 4, 8, 12 would be somewhere there, and so on. At the very top, since this is the power set of n, obviously everything is contained in n, right? So this will be at the very top, and it will be something like this. Which elements, which sets would be right below it? Well, we can take in and just remove one element, right? Remove 0. Maybe we can just remove 1. And by the way, you will notice that this is not a line, right? This is not a linear order like the natural numbers themselves with their usual order. You can say 0, smaller than 1, smaller than 2, and so on. This is not a line. It's a more complicated structure. For example, the singletons 1 and 2, these I cannot compare them, right? None of them is contained in the other. These are actually disjoint sets. There's no way to know which one is bigger or smaller with this particular order, right? So I have to write them parallel to each other, sort of horizontally, to illustrate that it's not the case that one of them is bigger than the other. Hopefully this makes some sense. So if I go even lower, I would have something like n minus 0 and 1, and this one is actually contained in these two, and so on, right? There's a bunch of examples. Oh, okay, that's a really interesting question. So Yang asked if partial order like trees. So a tree is an example of a partial order, that is correct. But this thing I'm writing here is not a tree. And you can easily see why this will never be a tree. It will never be a tree as long as the set has at least two elements. That's an interesting exercise. But you can see why, right? So take two elements right here, take the smallest and take the biggest, and those form a cycle. Those already form a loop. So this can never be a tree. But it is true that there is a way to talk about trees, and partial orders are trees. Sorry, the other way around. Trees are partial orders. Okay, let me make a quick pause. Let's say 10 minutes so you can grab some water. I will pause the... Okay, so I agree that the structure you can see here doesn't have a linear order, doesn't have a strong order like the natural numbers where everything is neatly organized on a line. But it is far from chaotic, right? There's still obviously some very interesting structure going on here. Now, maybe one more comment that I will not write down, but just for you to keep as a reference and to compare this with other examples that we will see in the past, sorry, in the future. The singletons have an interesting property, and that is that there's nothing beneath them except the obvious thing, which is the smallest element, the empty set. This property is called minimality, right? These are the minimal elements or the atoms, right? Atoms in that they are indivisible, right? You cannot split them into smaller things. So these are like the atoms of the structure. Similarly, if you remove a singleton from the big set, then these are the maximal elements. There's nothing above them except the obvious, which is always x. X is always, this is the family of subset of x. So of course, X will be the biggest one of them, right? So this lattice, this order has a minimum element. It has a largest element. It has minimal and maximal elements. And there's a bunch of things going on in between. Okay, so someone's asking what the this diagonal means. Right, so I defined this right here. Okay, at the top of the screen, you can see the set difference is denoted by that slash. So I'm removing one set from another. So that's all natural numbers except 0. And this one right here is all natural numbers except 1, and so on, right? Another thing I want to point out is that if you were, this might be a bit abstract, but if you were to remove the labels from the lattice and you turn it upside down, it will look exactly the same, right? Because these are behaving like singletons. They're just the complements of singletons. Okay, so let me add a little bit more detail to what I'm saying here, maybe a little bit more abstract. So in general, how do the operations come into play when I'm thinking about this? This will make more sense in the next few chapters because right now this seems like a weird example of a lattice, but there's other lattices. For example, the divisibility lattice that we will talk about in the next chapter, which will be, I think, in 2 weeks from now. The integers are ordered by divisibility, and they also form a lattice that looks very similar to this. You could even start thinking, what are the atoms of that? What are the indivisible elements of divisibility? and those would be like the prime numbers, right? But it will be very different from this one. So I want to contrast that in the future. Okay. Okay. So in general, how does this look like? If we zoom in, at the top, you always have the big set X. At the very bottom, you always have the empty set. And in the middle, well, no one knows what happens, right? But let's say we have some set A, and let's say we have some other set B. And of course, B has to be smaller than X, so I can draw a line. A has to be bigger than the empty set, or at least the empty set, so I can draw a line there. And I don't know if A and B can be compared with one another. Let's not worry about that now. Actually, now that I think about it, this is not a good way of drawing this. I want to draw them like this. Let's say that I don't know how A and B compare. Maybe they're disjoint. Maybe there's no way to compare them. But we know that they will form like a prism like this, right? So my question to you is, A and B always meet. If you're standing on A and B and you walk upwards, you will always meet, right? You will always meet at capital X, but maybe you meet sooner, right? Maybe these paths join before you get to X. And think about what that means abstractly, right? It means that there is a set that contains both A and B, but is still not capital X. Of course, capital X contains both, and so it contains everything about A and B. But maybe these join sooner, right? For example, let's say that A and B both fail to contain the number 0. Well, then they will both be contained in X minus 0, right? In the previous example. Okay, here's a really good question. Can we predict how many vertices this diagram will have? Yes, we always know exactly the number of vertices. This is something that we can prove. Actually, this would be a nice exercise to prove on Monday because it's something we need induction for. The number of vertices is always 2 to the n, where n is the number of elements of X. And this is true not just with finite X, it's also true with infinite X, but of course with infinite X, 2 to the infinite will not make any sense until we get to the chapter called infinity. So that's a really good question. Yeah, we can, that's the number of vertices. Okay, so similar to the question that I just asked, if you start if you start walking south from A and B towards smaller and smaller sets, eventually these will meet in the empty set because the empty set is contained in everything. In particular, it's contained in A and it's contained in B. But maybe these two join paths sooner, right? For example, what if A is equal to B? Well, they are already meeting in their own vertex, right? Hopefully this makes sense. So my question to you is, what is the soonest that these paths will join? If you have taken a course of calculus before, you may have heard of the smallest upper bound or the what is this, the largest lower bound, right? The supremum and the infimum. And this is exactly that. This is exactly the same idea. So take A and B. Together they have a bunch of upper bounds. For example, X is an upper bound because it is above both of them. But what is the lowest upper bound? Does that even make sense? So what is the soonest, what is the first instance that they will meet in this diagram? And also, what do you think this should be down here? What is the biggest set that is contained in both A and B? Is the question clear? What I'm asking you is, what is the smallest set containing A and B? And what is the biggest set contained in A and B? That's a perfectly reasonable question. Okay, and already see an answer in the chat. So that is correct. The union is the smallest set that contains A and B. Why is it the smallest set? Well, because if you remove anything, you're already removing things from either A or B, right? So you cannot remove a single point. It's the smallest it could be. And similarly, A intersection B is the biggest set contained in A and B. You cannot add anything to it because whatever you add cannot be in both A and B at the same time, right? because the things that are in both at the same time is the intersection. So the intersection plays a role of the supremum, sorry, the infimum in this context, and the union plays a role of the supremum in this context. This might be a little bit hard to relate to the supremum and infimum you see in calculus, but I promise it's the exact same thing. It would just look a little different because here this is not a line, right? This is kind of weird. So this type of structure where you have an infimum and a supremum is called a lattice. That is everything that a lattice is. Now, of course, the lattice I'm defining here has a lot more interesting properties. And if you're interested in that, I'm happy to provide references for lattice theory. We will contrast this with other lattices in the future. Particularly the divisibility one is an interesting thing. And one question that you can think about is how they are all related. There's clearly a sort of unifying theory going on here that I will not go into too much detail. But this is one example of how abstraction can help understand very concrete things better, right? You don't need to know what a lattice is to understand how to divide numbers and how to define a prime number and so on. But if you know what a lattice is, it gives you so much more insight as to how they behave. And if you think about prime numbers as the atoms of a lattice, this will give you a lot of information that will summarize more than half of the part on a number theory that I intend to cover. Any questions about union, intersection, and containment, or does this more or less make sense? Okay, so A union B is the smallest set containing both, and A intersection B is the largest set contained in both, right? So maybe I can add it like this. So A intersection B is always contained in A, and it is also always contained in B. The comma represents an and, right? This is two sentences wrapped in one. That's what the comma represents. A is also always contained in A union anything, and B is always contained in something union B. So this is always true. A and B are always between the intersection and the union. What I'm trying to convince you of in this lattice thing is that this chain of containments is wrapped as tight as possible. You cannot make this any tighter in general, right? There is nothing that, oh, what happened? There's nothing that you can write in between, right? There's no set here, strictly in between in general, that you can always guarantee will always be the case. Obviously, in some cases it might. And there's also nothing in between here. So this is very, very tight. And of course, the union is always contained in X because all of these are subsets of X. And this is always containing the empty set because it contains everything, right? So this is what the diagram represents just written in symbols. The subset of A intersect B is far away from A and B compared to A and B. Okay, so I'm not sure I understand the question. So if we compare A intersection B with A and B and compare that with a subset of A, right? So any subset of A has to be on this branch somewhere, right? All subsets of A. Actually, the set of subsets of A forms like a sublattice. It forms the same structure, but like zoomed in, like contained in the bigger one. That's what all the subsets of A look like. So there's another copy of the entire lattice hidden under A, under any set, actually. Okay, so let me maybe give you a minute more to ask questions if there's anything that's unclear about this example. I think this is a nice summary of almost everything we've seen so far. Okay, so let's move on to the next topic, which is still part of this, and I will be writing more proofs with this. And we already saw what a relation is, right? A relation is any subset of the Cartesian product that you can right now see at the top of the screen. Any subset of that is a relation from A to B. But right now I only care about one specific type of relation, which we will call functions. And a function is a relation for which any element of A corresponds to a unique element B in B, right? And we abbreviate this phrase that there is a relation satisfying this and that with this symbol, right? Oh, sorry about that. With this symbol. This symbol means f is a function from A to B. A and B don't have to be non-empty. F doesn't even have to be non-empty, right? Nothing here, everything here could be empty. Yes. Yeah, the empty relation is a function, right? As we will see in a second, depending on A. So that's a good question. We don't require anything to be non-empty. Okay, since there's a unique element B that's related to every A, we can call this something in particular. It has to depend on the relation F, and it has to depend on the element A. So why don't we call it F of A? As I'm sure you've seen this notation used in the past to denote the image of A, right? What else? The set A is called the domain of F. It's everywhere that F is defined on. And B is called the codomain. It is whatever things land on or land in, I should rather say. So let's look at some examples. Then I will make some diagrams, and we will probably spend the rest of our time just working through some examples, maybe some easy proofs on understanding what a function is abstractly. I'm sure you've all seen functions and you've all used functions, but maybe you hadn't wondered how functions are defined in a more abstract sense. How do you know that something is a function or not? Okay, so here I have 4 examples of relations from the set 0, 1, 2, 3 to the natural numbers. And my question to you is we need to decide which of these are functions and which are not. The notation might seem odd because I'm just writing it out very like raw, it's just the tuples, the pairs. Generally, I won't go through all the trouble of writing it like this. I will write it in a more friendly way, but this is just to illustrate the definition. So what can you say about example number 1? Is that a function, is it not, and why? Okay, so would the relation function be bijective? I haven't defined what bijective means. Bijective is a stronger condition on a function. Being a function is, in a way, saying that the inverse relation is injective, is well defined. But I haven't defined injectivity or surjectivity or bijectivity. So this is more general. Maybe I can make a diagram first, and then we can look at the abstract example. Okay. So let's see if this works. Kind of. Okay, so what is a function then? So the idea is the following. We have a set A, we have a set B. They don't have to be different, they don't have to be empty, non-empty, disjoint, nothing. There's just any 2 sets. This one contains a bunch of stuff, this one contains a bunch of stuff. Any relation is just a pair, just pairing them up, right? You can just take some element here and pair it up with this element. Relations are directional, of course. Maybe I don't need to add it as an arrow, but it doesn't really matter. So you can pair them up. Now they don't have to be bijective, right? Like I said, you could pair multiple elements here on the same side. What else? Oh, you can leave elements without pairing on the right side. The way I define function, which might be different from other textbooks, is that everything on the left, the domain A, must be paired up, right? I cannot leave anything empty here. That's just the way I defined it. You don't have to define it this way, and it varies, but it helps to keep track of what the domain is. And I don't really want to go through the trouble of defining a million different symbols. So I will just assume that A is always the domain of f when I write it that way. Okay? So everything in A must be paired because the function will have to assign something to everything. Now, every in B can have things that are unpaired. That is perfectly fine. You can pair multiple things in B to different. Sorry, you can pair the same element in B to multiple elements in A. What you cannot do is this. You cannot assign to the same element of A more than one element of B, because then this is not well defined, right? If this is A, then which of these two should be f of A? This doesn't make sense, right? F of A is supposed to be a unique element. So this is forbidden, right? We cannot do something like this. And that's what a function is. A function is just an input and an output, but the output is uniquely determined by the input, otherwise it's useless. Otherwise, there is no way to know what the output is going to be, right? You could all have the same output, that's okay, but everything should have a well-defined input. That's what a function is. Does this make sense? Or should we look at the examples? So which of these are functions and which of these are not? What about number one? Is number one a function? Why is it not a function? It is defined everywhere in the domain, right? I'm assigning something to 0, something to 1, something to 2, something to 3. So that part is satisfied. Okay, exactly. Okay, I see, you get it. Okay, very good. So I have two outputs for the same input. Okay, I think that's literally what Dennis said. Great. So 0 is mapped to two different things. So f of 0 is not well defined, right? Now, it might seem a little weird maybe writing a definition this abstract. You can say, I mean, do we really have to define it this way? We all know what a function is, right? But it turns out that sometimes, and I've seen this happen many times, the very common mistake, you define something that is not really a function and you treat it as a function, and then you make a mistake and you arrive at things that are nonsensical. So there is actually risk of defining things that don't quite work. And we will look at examples of this when we move on to more maybe advanced set theory. What about example number 2? Should be writing the answers, maybe. Okay, example number 2 seems like it's a function. And you can just check, right? Every element of the domain has an output. Yes. Is that output unique? Yeah. I mean, the inputs only get mentioned once, so this has to be true. Okay, great work. What about number 3? Yeah. Yeah, okay, great. I think we got this then. Number 3 is a function. Like I said, there's no problem with all inputs having the same output, right? This is actually called a constant function, as I will define in a second. And you can probably quickly say if number 4 is a function or not. Right, so number 4 is not a function simply because the domain is not covered. So maybe I can say, I haven't defined what the image is, but the image is just f. Maybe I can say this. Is not defined, right? Either it has no output or it has multiple outputs. Either way, it would be not well defined or not defined at all. Okay, let's look at some more abstract examples, maybe not with numbers. So the first one is an abstraction of example number 3 above. If you take an element C in Y, which is the codomain, and then you take x cross c, that is all the pairs of the form x comma c for some x in capital X, then this is called the constant function. It's the constant c, right? And it is a valid function from x to y. This always works. This is always a function. In the second example, if you take all the reflexive relation, the diagonal basically, x comma x, this is called the identity on x. Let me maybe add a few things here for notation. So if f is this function, then f of x is always defined as c, the constant c, right? With the more modern notation, perhaps. The identity, if we call this function f, well, this is just, it sends everything to itself. That's why it's called the identity, right? Because the identity is who you are, it's yourself, right? Okay, one more example. If a is a subset of b, then the function that maps a to b and just maps every element to itself is called the inclusion map. And I just want you to pay attention to the fact that the inclusion map and the identity are different things, even though they are defined the same way. They are different things because if you look at them as sets, those sets are generally different unless A is equal to B, right? So make sure you understand that a function is not just the formula f of x equals something that defines the function. Part of the function, if you scroll up to the definition, part of the function, an essential part of the function is the sets A and B, right? The domain and the codomain are an essential part, and if you change those things, you get a different object. And this might not seem very important now, but it will be important, right? So if you make sure you understand these details. So the inclusion map and the identity are different, even though both seem to have the same definition. Okay? These will become more relevant in the future as well. Do you have anything else? I don't. Okay, so let's look at some more examples and maybe some general properties of these. So definition. This is where things start to get more interesting. So let f be a function from x to y. Like I said, this symbol abbreviates that x is the domain of f and f is a function from x to y, right? So let f be that. Let's see, what else do I need? Okay, some textbooks say A has to be a subset of X. That's not really necessary. Be any set. Then I want to define the image. The image, actually, this is related to something that someone asked on Piazza. They pointed out a typo in the problem set, which is now fixed. I just want to write this. So the image of A under F denoted F square brackets. Okay, many textbooks use the normal brackets. I think that's a terrible notation because if you use regular brackets, you don't know is A the input or is A a set of inputs? And it might be clear if you're talking about real numbers and real functions, but what if you're talking about functions that map from sets of sets, like a power set, right? What if you have this situation? I don't know, 0, 1, whatever. Then f is mapping functions. Sorry, f is mapping sets to things. So if you use regular parentheses, it's completely ambiguous if you mean I'm applying f to the set of inputs or I'm taking that set as the input itself. Okay? I could give an example of why this notation is actually ambiguous and produce a contradiction if you wanted me to. But if you don't know what I mean, then it's not too important. All I want to highlight is that we will use square brackets to distinguish when I'm applying f to a set or to a single element of the domain. So what is this set equal to? This is the set of all y's in y such that there exists an x in x that gets mapped to it. F of x is y. Sorry, of course a, right? Okay, Let me see how I can write this in a more clear way. The set of all such that there is an x in A such that xy belongs to F. Why am I writing it like this? I don't know if A is a subset of the domain or not. A might be something nonsensical for which F is not even defined, but this definition would still make sense. And like I said, this relates to something mentioned in the problem set. Let me give you a simpler variant. So if I do assume, let me write this maybe just for clarity. If I do assume, which I will generally assume, that A is a subset of the domain of X, then the image of A is just F applied to every element of A, right? This is a lot simpler. But this symbol right here only makes sense if A is indeed in the domain. So if it isn't, which I might find useful in some circumstances to use the same symbol, if it isn't an element of the domain, I cannot use this notation, so I have to do something more abstract, like the one on the sentence above, right? So similarly, so this is definition one. Similarly, for B, a subset which we would typically think of a subset of Y, the inverse image, and again, this is not the inverse function. I don't know if F even has an inverse. This is the inverse image, right? It's a set. It's something different. So this will be the set of all x in X, such that when I apply F to it, now this makes sense, right? This is a lot easier to define actually. If I apply F to it, it lands within B. And X is in the domain, so f of X makes sense, and B doesn't have to satisfy anything. Some textbooks will say, well, but B has to be a subset of the codomain. Well, not really, right? We don't care. Like the definition makes sense without it. So why not leave it in a more general way? Let's make a sketch. I promise this will make a lot of sense. So this is X. I'm calling it X now. So this is the set X, and this is the set, let me move the chat. This is the set Y, okay? And I have a function that maps X to Y. If I have a subset A, all I have to do to find the image f of A is take every point here and see where it lands. Every point here and see where it lands under F. Every point here and see where this one lands, right? The set of all the points that get hit by F, that is f of A. That's the image of A. And the inverse image is the same thing. I just have to draw the arrows in the opposite direction, right? Now, when I say the same thing, we have to be a little bit careful. They have different properties, right? The inverse image and the forward image behave slightly different. Now that I realize I didn't write inverse image. Okay, so this is called the inverse image. Inverse image, right? Let's just do some quick examples and then we can end a little bit early today. Okay, so examples. Let's make them maybe more concrete. So let's say that f is a function from the naturals to the naturals. What happens if f is the constant function, right? Let's say f is the constant function 0. What would be f of, say, the even numbers? So 0, 1, 0, 2, 4, and so on. What is the image of this? Here's another example. What if f of n is just the identity, right? So this is the constant. This is the identity. What is f of? Same set, 0. And also, what is the inverse image of, I don't know, let's say 0? What is the inverse? Sorry, let me call this different things. G, G, G. Okay, so I got some answers in the chat. So for the first one, the image is 0, right? Okay, that seems right to me. So by definition, this is just f applied to 0, f applied to 2, f applied to 4, and so on. But all of these elements are the same because f is constant, right? This is all just 0, 0, 0, 0. And I don't have to write repetitions in sets. Sets absorb repetitions because it's the same set, right? Okay, good job. What about this one? What about this one? 0. Just write any answer that you have. Feel free to write it down. Let's see if I can make more space. One. What is the inverse image of 0? N, exactly. Everything goes to 0, so the inverse image is 0 because everything in N gets sent to 0, right? What is the inverse image of 1? It's the empty set. Nothing hits 1 because it's a constant 0, right? So nothing hits 1. And this brings me to the point that all these things could be empty, right? The image can never be empty unless I take it on the empty set, but the inverse image could be empty. So this is already evidence that they behave differently, and there's way more than that. Okay, what about the example G? What would this set be? Maybe I can just write it 0 G, G of 2, just apply it to all these elements, and G disappears. It just gives me back the same elements, right? So okay, this is the same set. Nice. What about the last example down here? What is the inverse image of 0? That would just be the set containing 0, right? There's no other element that when I apply G to it gives me 0 because every element gets mapped to itself, right? So you can work through some of these examples in your own time. Maybe try proving them, writing a formal proof for them. So let's say proof is exercise. They are very interesting exercises, right? Just applying the definition. Okay, so next lecture we will talk more about natural numbers, maybe cover some more examples on functions if it helps, although many properties have already been mentioned before. So I will stay here for a few minutes if you have any questions for me, but if you don't, then this is the end of the lecture. Let me stop the recording.